Since ancient times, human beings have dreamed of conquering the sky. From Leonardo da Vinci's sketches to the 18th century hot air balloons, the idea of flight has fascinated both inventors and scientists alike. In the 19th century, figures such as George Cayley and Otto Lilienthal took a further step by studying aerodynamics and building gliders capable of sustaining themselves in the air for brief moments. But the true challenge was not only to rise, but also to remain in the air with control and autonomy. How did humanity progress from simple fabric gliders to constructing metal giants capable of crossing oceans in just a few hours? The first great breakthrough did not come immediately. For decades, attempts to equip aircraft with an efficient propulsion system failed, until in 1903, the Wright brothers achieved what had seemed impossible until then: an airplane capable of taking off, remaining airborne, and landing under human control. Their fragile biplane made of wood and fabric barely covered a distance of 36.5 meters in its first flight, yet its impact transcended any temporal mark. In less than half a century, aviation ceased to be an experiment and became the basis of an industry that would shorten distances and transform global trade. The challenge was no longer just to fly, but to do so efficiently, safely, and on a large scale. The first attempts to turn aviation into a means of commercial transportation were rudimentary, with aircraft adapted from military models and limited routes. In the decade of the 19-teens, small companies began operating short-distance flights, primarily for mail transport. However, the need to connect cities more rapidly spurred the development of aircraft designed specifically for passengers. During the 20s and 30s, models such as the Ford Trimotor and the Douglas DC-3 established the first industry standards, improving load capacity, range, and flight safety. By the mid-20th century, the consolidation of airlines and the expansion of airport infrastructures allowed commercial aviation to become a viable alternative to land and maritime transportation. With the arrival of jet aircraft in the decade of the 1950s, the speed and efficiency of air travel reached a new level, shaping the industry that today mobilizes millions of people around the world. Once commercial aviation was consolidated as a means of transportation, airplane design underwent significant transformations, driven by the need to improve efficiency and safety. The evolution of jet aircraft in the 1950s not only increased their speed, but also required radically new design methodologies. As the industry matured, advances in materials, propulsion, and automation allowed airplanes to become more complex and adapted to the growing demands of passengers and the global economy. Today, creating a commercial airplane involves balancing physical forces, advanced materials, and international regulations, a process that begins years before the first piece is manufactured. With the constant evolution of commercial aviation, operational demands progressively transformed airplane design, pushing the industry to adopt increasingly advanced approaches. The design process began with a series of key requirements: passenger capacity, range, and efficiency. Aerodynamic engineers began employing three-dimensional airflow simulation software, a technology that allowed optimizing the shape of the wing until reducing aerodynamic drag by 15%. This innovative approach led to designs such as the wing profile of the Airbus A350-900, whose millimetric curvature generated enough lift for 280 tons of weight with a wingspan of 64.75 meters. As technology advanced, the structure of airplanes became more robust and precise thanks to improvements in simulation. Structural calculations were performed using finite element models, a technique that allowed predicting stresses at thousands of critical points. For example, the fuselage of the Boeing 787, built with carbon fiber composites, was designed to withstand pressures equivalent to 8.6 tons per square meter during depressurization, meeting international safety standards. At the same time, systems engineers worked on integrating tens of thousands of electrical and mechanical components, from control surfaces to entertainment systems, ensuring that each subsystem could operate under extreme conditions, from below zero temperatures to intense heat, under rigorous environmental testing standards. This level of precision and collaboration extended throughout the entire development process. Collaboration became a key element. Teams of thousands of specialists, from combustion experts to interior designers, began working on integrated digital platforms, where every change to a wing flap automatically updated the production drawings. This multidisciplinary approach, combined with wind tunnel tests and virtual prototypes, allowed reducing the development time from 10 to 6 years while maintaining extremely low error margins. But this collaborative approach was not limited solely to design. It also extended to manufacturing, turning airplane production into a global puzzle where every piece, from a screw to a complete wing, was produced with sub-millimetric precision on different continents. In 2011, the Boeing 787 Dreamliner marked a milestone by integrating components from 45 countries. The wings, molded by Mitsubishi Heavy Industries in Japan. The horizontal stabilizers, manufactured by Alenia Aermacchi in Italy. And the fuselage, assembled in South Carolina, United States. This system, based on a design for manufacturing philosophy, reduced costs and lead times, but demanded logistical synchronization with no margin for error. The final assembly took place in mega plants such as the Airbus facility in Toulouse, where autonomous KUKA robots worked alongside human operators. These robots, equipped with measurement lasers with a precision of 0.005 millimeters, drilled 3,000 holes per wing in 12 hours, a process that in the 60s took weeks and generated up to 25% waste due to errors. For critical parts, such as the wing spars of the Airbus A350, 5-axis milling machines were employed to carve 8-ton blocks of titanium, removing 7.6 tons of excess material in 40 hours. However, precision in manufacturing would not be enough without a rigorous quality control process to ensure the safety of each component. Quality control for building commercial airplanes is relentless. Each component undergoes non-destructive testing according to international ASTME 2375 standards. Ultrasounds that can detect cracks of 0.1 mm in carbon fiber panels, while thermal cameras verify welds in engines. In 2018, a three-dimensional scanning system on the Boeing 777X identified a deviation of 0.03 mm in a wing joint, which was corrected before it could affect aerodynamics. Automation also reaches management. SAP software integrates data from 4 million pieces per airplane, alerting in real time about delays or defects. This approach, combined with assembly lines that blend robotics and specialized labor, allows assembling an Airbus A320 in 30 days, compared to the 150 days it took in the decade of the 1980s. The efficiency of a modern airplane is not limited to its assembly. Its true heart beats in the engines, where innovation in materials and design has reached extraordinary levels. The fan blades, manufactured in carbon fiber composites, rotate at 2,500 revolutions per minute, withstanding centrifugal forces equivalent to 100 tons. In the engine core, high-pressure blades, made with nickel-based superalloys and coated with ceramic, operate at temperatures close to 1,500 degrees Celsius, brushing against the melting point of steel. To guarantee their durability, engineers at GE Aviation developed in the decade of the 2010s an internal cooling system that uses microchannels to inject cold air, extending the lifespan of these components to tens of thousands of flight cycles. This advancement not only optimizes performance, but also reduces maintenance costs and improves operational safety. Sustainability has become a central axis of innovation in engines. In 2021, Rolls-Royce presented the UltraFan, an engine with a record bypass ratio of 11:1, which improves efficiency by 25% compared to previous models. This design, which diverts 90% of the air around the combustion core, not only reduces fuel consumption, but also significantly decreases noise, meeting the most demanding environmental standards. At the same time, sustainable fuels, derived from vegetable oils and waste, have been shown to reduce CO2 emissions by up to 80% under ideal conditions. However, their widespread adoption requires adapting combustion chambers to resist corrosion. a challenge that the industry has been addressing since the mid-decade of the 2010s. The GE9X engine, developed by General Electric for the Boeing 777X, is an emblematic example of these advances. With a diameter of more than 3 meters and a thrust of 510 kilonewtons, this technological giant is not only the largest and most powerful engine ever built, but also one of the most efficient. Its design, which includes carbon fiber blades and advanced cooling systems, allows it to operate with fuel consumption 15% lower than previous generations. Since its first test flight in March of 2020, the GE9X has set new industry standards, although its entry into service was delayed until 2023 due to technical challenges and the pandemic. These advances, along with the growing adoption of ecological fuels, are redefining the future of commercial aviation, making each flight cleaner, quieter, and more efficient. Alongside the engines, electronic and navigation systems play an equally crucial role, functioning as the brain that guides every aspect of the flight. The precision of a modern commercial flight is based on a network of electronic systems that process millions of data points per second. In 1983, the Airbus A310 introduced the glass cockpit, replacing analog instruments with digital displays and marking the beginning of integrated avionics. Today, the flight management system of a Boeing 787 calculates routes in real time, optimizing altitude and speed to save up to 2.5 tons of fuel on a transatlantic flight. Satellite navigation remains a fundamental pillar in modern aviation. Systems such as Europe's Galileo, operational since 2021, offer up to 0.5 meters of precision under ideal conditions, while Russia's GLONASS provides complementary coverage. These systems, along with X-band weather radars, capable of detecting storms more than 300 kilometers away, allow pilots to optimize routes and execute precise landings, even in reduced visibility. Fly-by-wire controls, now completely digitalized, are key in airplanes such as the Airbus A350 and the Boeing 787. Their signals travel at more than 100 megabits per second on dedicated networks, adjusting flaps and rudders in 50 milliseconds. Combined with software such as envelope protection, they ensure stability even in severe turbulence, protecting structural integrity and passenger comfort. Cybersecurity is an absolute priority for private jet companies. In 2018, Boeing implemented redundant systems in the 777X following cyber attack simulations. Since 2020, the FAA has required ADS-B, which transmits the airplane's position every second, reducing collision risks by 90% according to studies by the agency itself. These advances in safety and automation open the door to an even more ambitious horizon: full autonomy. In 2022, Airbus demonstrated in the ATOL project that an A350 can take off and land using artificial intelligence integrated with LiDAR sensors, multispectral cameras, and infrared technology. Although pilots remain indispensable, technologies like these are redefining safety standards, anticipating a future where human precision and automation converge to make aviation more efficient and reliable. Yet these revolutionary advances come with a monumental economic cost that only a few companies in the world can assume. The development of the Airbus A380, launched in 2007, required an initial investment of $25 billion, a figure that escalated to $32 billion due to technical and logistical delays. Each unit, with a list price of $445 million, implied a production cost estimated at $320 million, the result of a decade of research, composite materials, and an enormous number of specialized engineering hours. However, mass production mitigates these costs. The A320neo, currently manufactured at a rate of 60 units per month, reduces its cost per airplane to $110 million. According to data from Aviation Week, thanks to economies of scale and process optimization. Research and development costs represent a significant portion of the total budget. Boeing invested $32 billion in the development of the 787 Dreamliner according to reports from 2011, including overruns due to delays and failures in lithium battery systems in 2013. These tests subjected the fuselage to 150,000 pressure cycles, equivalent to 3 times its estimated service life. These expenses are only amortized if at least 1,300 units are sold, a threshold that the 787 surpassed in 2020. On the other hand, specialized labor accounts for around 25%. Assembling an A350 requires 3,000 workers in Toulouse, with average salaries of 75,000 euros per year in Europe, compared to $85,000 in Boeing plants in Seattle. Certification is another critical expense. The FAA and EASA require up to 2,500 hours of test flights, with costs that can exceed $1 billion per model. For the A350, Airbus conducted 400 test flights under extreme conditions, from below 40 degrees Celsius in Canada to above 50 degrees Celsius in the United Arab Emirates. These processes, along with the manufacturing of non-reusable prototypes, increase the initial cost, but ensure that each airplane operates safely during its estimated service life of 60,000 to 90,000 hours. Airlines, for their part, negotiate discounts of between 40 to 60% when purchasing fleets. According to Bloomberg, Emirates paid $157 million for each A380 in 2018, compared to its list price of $445 million. This strategy, along with leasing, a long-term rental system that allows companies to operate airplanes without buying them outright, and maintenance options, enables companies to amortize their investments over time, an estimated period of 12 to 15 years. A vital calculation in an industry where, according to Airbus, a 2% improvement in efficiency translates into $1 million saved annually per airplane. These efforts to optimize costs and efficiency not only seek to improve the present, but also to pave the way for a more sustainable future for aviation. The industry has committed to achieving net zero CO2 emissions by 2050, using ecological fuels and innovative technologies. One example is the electric airplane Aviation Alice, which in 2022 managed to fly 440 kilometers with lithium batteries. Airbus, on the other hand, is working on a hydrogen-powered airplane that could be ready by 2035. However, adapting airports for these technologies will require significant investments, as the necessary infrastructure is still under development. Countries such as Saudi Arabia are also investing in the future of aviation, with projects that combine innovation and sustainability. As part of its Vision 2030 initiative, the Kingdom has announced plans to build airports powered by renewable energies. In addition, the mega project Eniom includes a smart airport that will use artificial intelligence to optimize operations and reduce emissions. Although these projects are still in the development phase,